A reasonable question to ask is why we need this matrix-based method for solving systems of equations. Previously, we've talked about substitution and elimination, so why the need for a third method? Well, one reason is that for a system like this one, where we have 4 equations, we would have to start, if we were to use substitution or elimination, we would have to start by choosing 2 of these equations and eliminate one variable. Then we would have to choose another pair of equations and eliminate that same variable, and then choose a third pair of equations and eliminate that same variable. Or essentially, reduce this system of 4 equations down to a system of 3 equations. Then reduce that system down to 2 equations and solve that system of 2 equations. As our system gets larger and larger, that can become very, very cumbersome. So what's nice about our approach for matrices is that the method stays the same regardless of how large our system gets. And we'll walk through that as we look at this system of 4 equations. So converting our system of equations into an augmented matrix follows the exact same process that we've used before. In equation 2, we have a missing term, so we'll put in that placeholder 0. All that's going to change is that our matrix has an additional row and an additional column. Apart from that, our process is identical to what we've done for our previous examples. We start with row 1, column 1, and convert that into a 1. In this case, we already have that. So what we'll look at doing is simultaneously zeroing out all 3 values below. So we'll update row 2 by taking -2 times row 1 plus all of our values in row 2. We'll update row 3 by taking -3 times our values in row 1 and adding that to row 3. And we'll update row 4 by taking -1 times our values in row 1 and adding those results to our values in row 4. Column 1 stays unchanged. The matrix operations or the row operations that we've established will knock out each of those terms below our 1, so to give us a 0 in rows 2, 3, and 4. And then the remainder of our rows will become -3, -1, -2, and -14 for row 2, -1, -2, -4, and -13 in row 3, and -3, -3, 1, and -10 in row 4. The next thing we want to do is get row 2, column 2 to be a 1. But rather than apply the same types of operations we've been applying, what I'm going to do is send row 3 to row 2. So I'm going to replace the position or switch the position of those 2 rows. So row 2 will become 0, -1, -2, -4, -13. And row 3 will become 0, -3, -1, -2, and -14. Switching the places of those 2 rows hasn't achieved the goal that we're after, but it does get us there in an easier way. Now all we have to do is take row 2 and multiply it by -1. if we look back a couple of steps, we also could have taken row 2 times negative 1/3. That would have achieved our goal, but we also would have ended up with a number of fractions. And I just prefer to keep simpler numbers, in this case integers over fractions. So now what we've done is updated row 2 so that row 2 column 2 is a 1 and we don't have any fractions. Now what we'll look at doing is zeroing out the values below that 1 we created. In order to do that, we'll look at updating row 3 by taking 3 times row 2 plus our values in row 3. And we'll update row 4 by taking 3 times row 2 plus our values in row 4. So the zeros at the beginning of those rows will remain unchanged. The values in the second column will both get zeroed out, and our remaining results will become 5, 10, and 25 in row 3, and 3, 13, and 29 in row 4. Now we need row 3, column 3 to be a 1. So we'll take 1/5 times all of our values in row 3 to update row 3. Changing these values to 1, 2, and 5. And our next step will be to zero out the 3 in row 4. In order to do that, we'll update row 4 by taking negative 3 times row 3 and adding that result to row 4. So we'll zero out that third value, and then the rest of that row will become 7 and 14. And then to turn that value in row 4, column 4 into a 1, we'll look at updating row 4 by multiplying it, all the values in that row, by 1/7. So this will turn our 7 into a 1 and 14 into a 2, which gives us our result, or our resulting augmented matrix, in upper triangular form, that row echelon form, on the left-hand side of that vertical bar. And from there we could apply backward substitution to get, in this case, our ordered quadruple, x, y, z, w, to be 2, 3, 1, 2. Again, applying the same process that we've used in the past to find those remaining variables. So our matrix method is a better method to apply as we get into larger and larger systems, because we don't have to think any differently about our process. We just apply the same algorithm over and over and over, which also makes these matrix methods a better method whenever we're trying to get computers to solve systems of equations. Computers are almost always designed with matrix-based methods because this process is more programmable, more algorithmic, regardless of how large our system becomes.